Okay, this is a sedimentation tank. So as usual in water treatment plant, you need to design sedimentation tank. So in sedimentation tank, okay, you can imagine that water entering the sedimentation tank from the flocculation tank with this flow rate. And the flow rate is labeled as Q. The dimension that is very important for sedimentation tank, the first one is the surface area. And we label it as AS. Okay, so this is the surface area of the tank. If you can still remember the photograph of the sedimentation tank, it's basically nothing. It's just a long, huge tank, like a football field or something. So the area, the bigger size of area is extremely important for sedimentation tank. So this is one dimension that you need to know. The second dimension that you need to know for the sedimentation tank is the height of the tank itself. Okay. We also have to remember once the water, okay, entering the sedimentation tank, there will be two type of speed that can be seen. Okay. Imagining water coming into the sedimentation tank and the water brings along particles. Oh yeah, I forgot to say about the detention time. Okay, right. Apart from the surface area and heights, the detention time is also important in the sedimentation tank. What do we mean by detention time? Is the time for the water to be inside the sedimentation tank, how long it stays, perhaps 1 hour, 2 hour, 1 day, 2 days, before it goes out to go to the next process, which is filtration process. Okay, so those three are the dimension or the variables that probably you need to know in the sedimentation topic. Right, I mentioned to you just now that when water enters the sedimentation tank, there will be two types of speed will be seen. The first one is the particles. Remember, the water brings along the particles. The particle itself has their own speed, and it is labeled as Vs or settling velocity. So I like to equate them with the speed of particles. So the particles is moving in the sedimentation tank with their own speed. Okay, we label it as Vs. Another speed that we need to remember that also exists in the sedimentation tank is the speed of water. So I label it with the blue arrow like this, not blue, yeah. This is purple. Purple arrow like this, okay. So this is the speed, or it represents the speed of the water itself. So you have different speed. One speed for water, and the other one is speed of the particles. Okay. So the speed of the water is labeled as V naught or overflow rate. Okay, the speed of water, V naught. Now then, I have a question to you guys. You know that there are two speeds in the sedimentation tank, one for particles and one for water. In order for the sedimentation tank to be effective, which one need to be faster? Is it the settling velocity or the speed of the particles, or is it the overflow rate itself or the speed of the water? Which one should be faster? Speed of particles or speed of water? Speed of particles. Okay, someone particles. Okay, so everyone seems to be saying the same thing. Speed of particles. Is that right? What do you think? Yes. Okay. So the answer is yes. Okay, the speed of particle has got to be very, very fast compared to the speed of water or the overflow rate. Okay, the formula for speed of the formula for the overflow rate is H divided by T or Q divided by AS. So H is the height divided by the detention time is equal to Q, the flow rate itself, divided by the AS, the surface area. So this is the formula for overflow rate, okay, or the speed of the water itself. Okay, the formal name of V naught is overflow rate. Okay, do not call it as the speed of liquid or speed of water, but to make it clearer or to make it for you to easily understand, so I call it as the speed of water, but the formal name is actually the overflow rate. Right. One thing that I want to say to you that this formula will never be given in the exam or in the test. It is something that you need to remember to memorize it. Not very difficult. V naught is just equal to H divided by T or Q divided by AS. This is the overflow rate. So right, at this moment, do you think it's clear, my explanation?
Yeah,